Hello everyone. Today we'll start design of shear in PSC members. So it is fourth module as per the syllabus of VTU. So in shear, when compared to RCC, somewhat it is little bit complicated in case of pre-stressed concrete members. So how we are going to consider the parameters, how we are going to analyze the members for shear, we'll discuss later. So before going to that, let us have some introduction about shear stress in PSC members. So in analysis, we will consider the shear stress based on few principles of mechanics. One is equilibrium of internal and external forces, compatibility of strains in concrete steel, constitutive relationships of materials. So if we analyze any member, conventional analysis means it is with respect to RCC. If we analyze, we'll consider only simple equilibrium equations like sigma fx, sigma fy and moment. Here in that case, the shear strain compatibility will not consider the constitutive relationships of materials like stress strain relationships will not be considered. Also, the strength under shear for the concrete is only based on the results. It is calculated thing, so it will be conventional analysis. So in beams, shear stress is generated due to two reasons. One is bending or twisting. If the shear stress generated due to bending, we will call it as flexure shear stress. If the shear stress caused due to torsion twisting, we will call it as torsional shear stress. So as per our syllabus, we are concentrating only on flexural shear stresses. So to understand what is flexural shear stresses, first we need to consider how the simply supported beam with the UDL will behave, and later the concept of pre-stressing will be added with the flexural shear stress developed in the simply supported beam with UDL. So for that, first we should know stresses in uncracked beam. So that is, the beam is in its original position or a good condition, so that will be treated as uncracked beam. So how the stresses will develop in that? The figure shows the following variations of shear in moment. So figure there in next page we have a figure. So if you observe this figure, you can see the variations of shear and moment along the span of the simply supported beam. So here, if you take the moment BMD, it will be in the parabolic variation, and SFD it will be triangular. The same manner along the cross section, the shear will vary. So normal shear vary in the triangular or linear, and variation of shear stress will be in parabolic form. So here the normal stress and shear stresses will generate 2D stress fields at a point, and the stresses in any point, 2D stresses in any point in the beam will be expressed in terms of principal stresses, and these principal stresses will be understood by using the concept of Morse circle. So when the beam gets cracked, before cracking, the steel is negligible. The stress carried by the steel is negligible. So when principal stress exceeds the cracking stress of the steel, the concrete get cracks, and there is a redistribution of stresses between concrete and steel. That is, the steel and concrete will balance the stresses. So for example, if you observe the figure, we have considered an element on the neutral axis and we consider it as 1. So in that element, the shear stress is maximum and normal stress is 0. So the principal stress, tensile stress, will be inclined at an angle of 45 degree with respect to neutral axis. For that we have one more figure. In this figure you can observe state of pure shear, it will be it will be perpendicular to along the plane, and principal stress will be inclined with 45 degree to the neutral axis, and by using Morse circle we can draw the stresses. So at the level of neutral axis, the normal stress is 0 and shear stress is maximum. That's what I said earlier. So the element at that level will be under pure shear. So there is no principal stress. It will be under pure shear, and it will having the biaxial tensile compressive stresses. So in one axis it will be under tension and another axis it will be under compression. So in figure you can observe sigma 1 will be tensile stresses and sigma 2 will be compressive stresses. So these principal stresses are inclined at 45 degree with respect to the axis of the beam, that is neutral axis of the beam. So we need to study these behavior of sigma 1 and sigma 2 to understand the cracking of concrete. The Morse circle representation of the state of in-plane stresses on surface of various inclinations passing through a point. So in this circle you can clearly understand the horizontal and vertical axis represent normal and shear stresses respectively. So horizontal axis sigma 1 and sigma 2, it is principal or normal stresses, and vertical represent shear stresses. So for a state of pure shear, the center of Morse circle coincide with the origin of the axis. So if you draw the Morse circle with respect to pure shear, the center of circle should coincide with the origin of the horizontal and vertical axis. So since shear force is maximum near supports, so if you observe SFD, you can clearly understand shear force is maximum at support. Cracks due to shear occur near the supports. So where there is a maximum shear force, the shear cracks will develop at that position. So the cracks formed around the neutral axis and perpendicular to the principal tensile stresses. So that is sigma 1. Tensile stresses are sigma 1. So for that, the cracks developed will be along the compressive tensile stresses, that is sigma 2. That means it is perpendicular to sigma 1. The cracks thus inclined at 45 degree to the axis of the beam. Again, so sigma 1 is inclined at 45 degree to the axis, and cracks are perpendicular to that axis stresses. So obviously the cracks will be inclined at 45 degree to the axis of the beam. So in figure you can observe sigma 1 is inclined with an 45 degree to the axis. So for perpendicular that in reverse way, the crack also inclined at an 45 degree to the axis of the beam. So for a point near the bottom edge of the beam, so in this figure you can observe we have considered one more point number 2, that is another element. So for that element, the normal stress is maximum. And shear stress is almost to 0. It may be equal to 0 or it is nearly 0. That is negligible shear stresses will be there. So the principal stress sigma 1 is almost parallel to bottom edge of the beam, the angle of inclination of sigma 1 with respect to axis of the beam is much smaller than 45 degree. So it is almost less than 45 degree. In figure you can observe. So sigma 1 is inclined with an angle of less than 45 degree with respect to axis of the beam. So adjacent to the bottom edge, the tensile stress due to flexure is maximum. So when bending is occurs, bottom stresses will be under tension. So in that case, the shear stress is 0. When there is a maximum flexure or tensile stresses, shear stresses will be 0. The state of stress is nearly uniaxial tensile stress, that is, stresses are acting along the axis. The principal compressive stresses are negligible. There is no compressive stresses. So sigma 2 is almost 0 where sigma 1 is maximum. So the Morse circle is shifted towards the axis of the principal tensile stresses. We know what we have considered: sigma 1 and sigma 2 along the horizontal axis and V along the vertical axis. So when there is a maximum tensile stresses and 0 shear stresses, the Morse circle shift towards the principal tensile stresses. Earlier, the center of the circle coincide with the center of origin of the axis. So since the moment is maximum at midspan, cracks due to flexure occur near the midspan. So when bending moment, if you see bending moment at midspan, there will be maximum bending. So because of that bending, obviously the cracks will occur at the midspan. The cracks are formed at bottom edge and perpendicular to sigma 1, same as in case of previous one. So but since sigma 1 is parallel to the edge, cracks are perpendicular to the edge. So since tensile stresses are along the axis, the cracks will be perpendicular to the axis. So in case of previous one, sigma 1 is at an angle of 45 degree. So in turn, the cracks developed are also at an 45 degree with respect to axis of the beam, as sigma 1 is perpendicular to the cracks developed. But in this case, sigma 1 is along the axis and cracks developed are perpendicular to the axis. So that you can observe here in this figure. So that is first thing, how the stresses will develop in the beam, in the uncracked beam. So next thing we need to know is what are the components of shear resistance. So the components of shear resistance are studied based on the internal forces at the flexure shear crack. The forces are shown in the figure below. So we have different forces here. So first let us start from top one, VCZ. So it is shear carried by the uncracked concrete. So concrete, shear force carried by the concrete. Next, VA, it is shear resistance due to aggregate interlock. So there will be bonding between concrete, cement and aggregates, and there will be interlock between number of aggregates. So because of that also some resistance for the shear stresses will develop. So that is shear resistance due to aggregate interlock. And VD, shear resistance due to dowel action. And VS, shear carried by stirrups. Shear reinforcement, what we call it as. Shear reinforcement why we provide, that is stirrups. So some shear stresses or shear forces will be carried by stirrups. Then vertical component of pre-stressing force in the inclined tendons. So that is VP. So the magnitude of the relative value of each component change with increasing load. So as the load varies, all these variables will change. So that is these are the components of shear resistance. So next, effect of pre-stressing force. Now for the normal RCC beam, if you apply the pre-stressing force, how it behaves. So in presence of pre-stressing force, the flexural cracking occurs at a higher load. For type 1 and type 2 sections, there is no flexural crack under service loads because we are designing these type 1 and type 2 within the limits of cracks. So type 1, we are considering there is no tensile stresses at the bottom, and in type 2 we are considering the loads such that there is just beginning of the cracks. Just when the crack starts to propagate, at that time, up to that time, we will consider the loads. So there is no cracks in case of type 1 and type 2 sections. So this will give us, or this is an example, best example for moment versus curvature curve for a pre-stressed section. So in presence of pre-stressing force, web shear cracks also generated under higher loads. So when we increase the load beyond the cracking load, so that means the load when the cracks just starts to happen, when the beam just starts to cracks, so that is cracking load. So when we increase the load beyond that cracking load, obviously the cracks will generate as in case of type 3 sections only, but the inclinations of the flexural cracks and web cracks are reduced depending on the amount of pre-stressing and the profile of the tendon. So the cracks developed in the section will, how much it will propagate or how much it will penetrate through the section, that will be depend on the what is the amount of pre-stressing force we are applying for the section and what is the tendon profile we have provided, whether it is parabolic or triangular or trapezoidal or straight tendon. Based on these profiles, the shear cracks developed will propagate in the section. So if you observe the figure, the effect of pre-stressing force is explained for a beam with concentric effective pre-stressing force. So the tendon is straight and passing along the neutral axis or axis of the beam, so that is concentric pre-stressing force. So for a point at neutral axis, what we have considered as a element number 1, so there is normal stresses due to pre-stressing force. So when we apply the pre-stressing force, obviously the section will be under compression, so that's why we have considered here as negative force minus FPE. So that element 1 will be under normal stresses. The principal stress sigma 1 is inclined to the neutral axis at an angle greater than 45 degree. So the angle between sigma 1, that is principal tensile stress, is greater than 45 degree with the combination of shear stress. The principal compressive stress sigma 2 is inclined to the neutral axis at an angle much smaller than 45 degree. So obviously the principal tensile stresses and principal compressive stresses both are perpendicular to each other. So when principal tensile stresses are inclined with an angle more than 45 degree, obviously the compressive stresses will be inclined at an angle less than 45 degree. How the angle with respect to sigma 1 increases, the angle with respect to sigma 2 decreases. So in this figure you can observe the state of plane stresses. So FPE, it is effective pre-stressing force. So sigma 1 is the principal tensile stress and sigma 2 is the principal compressive stress. So in this, the Morse circle shifts towards principal compressive stresses. So you can observe in the figure, the Morse circle shifted towards the principal compressive stresses. So in next figure you can see formation of cracks for a pre-stressed beam with large span due to span to depth ratio and uniformly distributed loading as shown. The figure can be compared with the reinforced concrete beam. So earlier case we have considered concrete beam and now it is pre-stressed beam. So after cracking, in presence of pre-stressing force, the length of crack width of a diagonal crack are low. So the length of cracks developed will be low. Thus, the aggregate interlock and zone concrete under compression is larger as compared to a non-prestressed beam under the same load. So that means the interlock, the resistance due to interlock and the hardened concrete at that particular zone is larger when you compare it with non-prestressed beam under same load. So if you are not applying the pre-stressing force, the strength due of interlocking of aggregates and concrete will reduces. So when you applied the pre-stressing force, the interlock strength also increases and zone concrete also increases. Hence, shear strength of concrete increases in presence of pre-stressing force. Obviously, the strength increases, and this is accounted for expression of VC. So next, factors reduce intensity of shear in PSC beams. So what are the factors we need to consider to reduce the shear in PSC beams? So we know that in case of RCC members, when subjected to superimposed loads or live loads, shear forces are developed at all the sections in the loaded member, that is from support to one support to another support. Wherever you take the sections, there will be shear stresses and there will be developing a shear stresses. So due to these shear forces and shear stresses are introduced in the member. So shear stress will be near to neutral axis and is minimum at the extreme fibers. The shear stress at any depth in the cross section is calculated using the equation tau equals Fa y bar by Ib. So here F is the shear force developed in the section in terms of kilonewton, Ay bar, so it is area into centroidal distance of that particular area. So moment of area above the level at which shear stress is required about the neutral axis. I moment of inertia as we know, and B is the width of the cross section with a shear stress at which shear stress is required. So the effect of this shear stress is induce the principal tensile stresses on the diagonal planes. Due to this diagonal tensile stresses, diagonal cracks are developed at the support section. So as we discussed earlier, the tensile stresses or sigma 1 principal tensile stresses will develop at an angle of 45 degree to the section. So that means it is a diagonal for the section, inclined stresses. So because of that diagonal tensile stresses, the diagonal cracks, cracks will develop in perpendicular direction. So diagonal cracks will develop. So to reduce these diagonal cracks, the diagonal tensile stresses should be reduced, or we should make it as a minimum, or if possible it should be come back to 0, and can be made compressive. So when it reaches 0 and further if we try to reduce, it will convert into compressive stresses. So this can be done by 3 different ways. One is horizontal or axial pre-stressing, vertical or transverse pre-stressing by inclined or sloping cables. So what are the factors which reduce the intensity of shear stress? So shear stress, factors which affect the shear stresses or which can reduce the shear stress in the PSC members are how much pre-stressing force we are applying for any member or any beam. So that is magnitude of pre-stressing force, then moment of inertia of the section, so width of the cross section, and type of pre-stressing, whether it is pre-tension member or post-tensioned member. So that also depend on the shear strength of the member. So here you can observe the principal stresses are calculated using the following relation. We have one equation to calculate the principal stresses sigma 1 and sigma 2. So for that we have equation fx by fy. First we need to calculate tensor fx and fy, then fx by fy by 2 plus or minus square root of fx minus fy by 2 whole square plus tau square. So if we want sigma 1, so that is maximum principal stress or principal tensile stresses, we consider it as a positive, that is plus. And if we want minimum tensile principal stresses or principal compressive stresses, we consider it as negative. So in pre-stressed concrete members, the direct stresses Fx and Fy being compressive and magnitude of principal tensile stresses is considerably reduced, and in some cases even eliminated. So when in some cases sigma 1 may be 0, so that under working load both major and minor principal stresses are compressive, thereby eliminating the risk of diagonal tension cracks. So this is about introduction to analysis of shear force. So here we have discussed about analysis of shear. So how the shear stresses will develop, how the principal tensile stresses will develop, how the principal compressive stresses will develop. Based on these stresses, how cracks are going to develop, what is the orientation of the cracks depending upon the principal stresses. These things we have learned, along with some factors which affect the development of cracks or development of shear stresses in the PSC members, and how to calculate the principal stresses sigma 1 and sigma 2 by using the relationship between of direct stresses. So in next class we will go for few more topics like modes of failure due to shear, limit state of collapse for shear, how code recommends the analysis of shear. These things we will discuss in next class. Thank you.